Chapter 7 Loops, or How to Spin Effectively. Many times in the course of programming, you will want to use the computer to do some task over and over again. This involves constructing a loop. In this chapter, we examine how a loop encloses a group of lines and repeats them a certain number of times. There are different kinds of loops, and we will explore each type. In this chapter, the loop, the counter statement, fixed iterative versus conditional loop, the for loop, the while loop, the do-while loop, examples with loops. What is a loop? Think of a cowboy using a rope to lasso a horse's neck. Visualize a circus ring or the balloon that encloses a cartoon characters through thoughts. Each of these is a loop. A loop always encloses something. When you think of a loop, you might have some of these images. See Figure 7.1. Figure 7.1. A loop around a horse's neck, a circus ring, and a loop around the thoughts in a cartoon character's head are all shown. A loop brings to mind a circular image. What does the term loop have to do with computer programming? We use the term to describe a part of a program that you execute over and over again until you are permitted to leave that part to get to another programming statement. In a sense, you continuously look back through the statements that you just executed, and you execute them again. Another image of the loop is one of going back to where you once were. Let's say you leave your house and go to your friend's house, but your friend is on her way to your house. You'll loop back to pick up your friend. In this sense, a loop means to go back to a place where you once were. To loop back to something means to go back to where you were and start again. See Figure 7.2. Figure 7.2. A person drives a car back home, loops back to pick up a friend who is standing next to the house. Loops in programs. Loops in programs. In a program, a loop describes a group of one or more lines of code that must be repeated some number of times. Consider this example. We are going to write a program to get 10 numbers from the user and check whether each number is even or odd. We need to get one number at a time from the user before checking to see whether it is even or odd. Then we go back to get another number to do the same thing. As we repeat each step, we go back to where we were in the program to repeat the same instructions. This is a loop. This loop encompasses 2 steps: getting the number, followed by the second step, evaluating it as even or odd. See Figure 7.3. Figure 7.3. The first and second step are shown. After a second step, we will go back to the first step, where we started, thus creating a a loop. Another way to envision a loop is to see it as a circle around a few lines of code. That way we have a clear understanding that everything within the loop circle will repeat as long as it should. I still have not mentioned anything about controlling a loop. For example, when does it end? How long does it last? These are natural questions that you should have when you first start learning about loops, and I will answer them shortly. Another control statement. The loop is another example of a control statement. When you stay in one block of code, a group of programming statements, to do something over and over again, you are controlling program flow. Just as I mentioned in Chapter 6, normal program flow is in sequence, executing one line after another. A loop forces program flow to stay on a certain line or in a block until allowed to exit that place and proceed in sequence. I will shortly discuss how a loop is entered or exited. Repeating steps in a loop. We make a decision to use a loop when we realize we want to do something over and over again on the computer. If you want to write the following sentence 1,000 times, I am sorry for chewing gum during class, your best decision would be to write a program that will print that phrase repeatedly. If you want to add up to 20 numbers, then you want to use a loop to get one number at a time, and then add that number to get to the tally of all the numbers so far. See Figure 7.4. Figure 7.4. Each programming statement is shown enclosed by a loop. Programming statement. Loop 1,000 times, print I will not chew gum in class. Loop 20 times, get a number, add the number to a sum. There are many examples of situations that use loops. Every time you enter an incorrect password at an ATM, the machine asks you to enter it again. The machine is actually executing a loop which, upon getting incorrect data, prints this message, your password is incorrect, please type it again. It will repeatedly print this message until you give it the correct password or it swallows your card. You can only get out of the loop by typing the correct data, or if the machine puts a limit on your number attempt. You can only get out of the loop by typing the correct data, or if the machine puts a limit on your number of attempts. See Figure 7.5. Figure 7.5. A loop is shown surrounding the body of instructions in the ATM situation. Loop until password is correct. Get input from user. If it's incorrect, print message to type again. A counter statement. In order to understand how loops work, we need to learn a preliminary statement that is used in most loops, and that is called a counter statement. A counter statement is a statement that allows a variable to increase its own value, usually by 1. For example, if a variable x has the integer 3 inside of it, after a counter statement is used with x, x will contain the value 4. How is this done? We write a statement to take the variable, in this case x, and add 1 to its present value. Then the statement assigns this new value to the variable x. So the statement has two parts, one that increases the value of x by 1, and another part that assigns that value to x. This is what it looks like. X left side, equal sign operator, x plus 1 right side. Think of the right side of the statement first. Adding 1 to x just gets the next integer greater than x. Assigning it to x gives x the new value. Assigning it to x gives x that new value. Once 1 is added to whatever is inside of x. If 3 is inside of x, then 3 plus 1 is 4. Now the value 4 is really what is meant by x plus 1. So 4 is assigned to x. X is equal to x plus 1. 3 plus 1 goes to x being a part of x. Another way to understand this statement is to consider the precedence of operators referred to chapter 2. The arithmetic operator, positive sign, addition sign, subtraction sign, multiplication, and the division slash, have higher precedence than the assignment operator, the equal sign. So 1 is added to x first, and then the result is assigned to x. Using the counter statement. A counter statement is used frequently in the context of loops to count the number of times a loop spins. Let's see how this is done. This statement is used in the same way that a ticket taker works at the gate of a concert. Every time a person walks through the gate, the ticket taker clicks the clicker to keep account of the number of people who pass through the gate. Count is equal to count plus 1. New count is equal to old count plus 1. Another way to think of this counter statement is to think of the variable on the left side as being the newest count. The newest count we have is the most recent value of the variable. It should get what is inside of count now, with 1 more added to it. New count gets old count plus 1. New count gets old count plus 1. See figure 7.6. Figure 7.6. Count is originally shown with the value 5. The addition is executed before the assignment that 6 is assigned to count, wiping out the old value of 5. Two different kinds of loops. There are two different kinds of loops in most languages. The main difference between loops is whether the loop is programmed to spin a run through a loop. A known or fixed number of times. Some loops can be designed to spin 15, 30, or even 100 times, for example. The programmer knows exactly how many times he wants to execute the loop. Other loops spin an unknown number of times at the time of writing the loop. These loops spin until something happens to stop them. Fixed iterative loops versus conditional loops. If you want to print a message 100 times on the screen, you use a fixed iterative loop. The term fixed implies that the number of times the loop spins 100 times is known at the time the loop is written. The word iterative means repeating. If you want to send a file to 50 people on a list, you know you will be sending the file out 50 times. That task should use a fixed iterative loop that we will execute 50 times. An example of a loop that spins an unknown number of times would be a loop that allows a player to play a computer game over and over again until he indicates he wants to stop playing. The programmer can't know ahead of time when the user will get sick of the game and want to stop playing. The player always asked at the end of a game is always asked at the end of a game, do you want to continue? Depending on the player's answer, the game playing ends, that is, the loop stops spinning. This is an example of a conditional loop. The loop spins until something happens, or, as we shall see shortly, until a Boolean condition becomes false. In another example, a loop controlling the number of times a game is played could depend on whether the player wins or loses. The loop stops when the player loses. As the programmer, you won't know ahead of time when the player will lose a game and be forced to stop. In both cases, the loop was exited when an event happened. That is, the player didn't want to play anymore or he lost. The loop spun until something occurred to stop its spinning. We either know that ahead of time how many times we want to do something, or we don't. Depending on our type of situation, we choose the appropriate type of loop. The first loop to examine is the for loop. The for loop should be used when you know how many times you want to do something. The for loop. The for loop is a fixed iterative loop. The loop will be used to do some tasks a predetermined number of times. Although its syntax varies from language to language, certain aspects of the for loop are the same. For one thing, it always has the word for mentioned at the beginning of the loop. The other characteristic of this loop is that you can figure out how many times it will spin before it is executed. Before you construct a for loop, you must decide what statement or statements you wish to iterate, that is, repeat. Well, then you need to know how many times you want to execute them. Once you decide, you can begin to construct the loop. You will need to declare a variable called a control variable that will aid you in the execution of the loop. The control variable's value is changed while the loop executes over and over again. When the control variable's value reaches the number of times the loop was set to spin, the loop ends. So now let's examine how the loop is constructed. The for loop has 3 key instructions in addition to the group of statements you wish to execute repeatedly, called the body of the loop. The first instruction is to declare a variable and assign it an initial value. The second instruction is to make sure that the variable is within range. We will compare it with some limit. The third instruction is to change the value of the variable. Before the third instruction occurs, the for loop executes the body of the loop. As an example, let's use a loop to print a message 5 times on the computer. First, take a variable y and set its initial value to 1. Now compare 1 with the upper limit you have in mind, say 5. To go into the loop and execute the body of the loop, printing the message. Next, take y and increase its value from 1 to 2. Now you're on your second spin. Go back to the second instruction, which is to compare the variable with our upper limit, 5. Since 2 is less than 5, we continue and go into the loop to print the message again. Next, increase y's value from 2 to 3. Compare 3 with 5 and continue because 3 is less than 5. You are only on your third spin of the loop. This process continues 1 time as y increases and becomes 4. Just before exiting, the message is printed again and y becomes 5. Then the number 5, the value in y, is compared with 5, the upper limit. This comparison triggers an exit from the loop because 5 equals 5, but is not less than 5. The loop is exited. See Figure 7.7. Figure 7.7. The variable y is shown with its old values crossed out and repeatedly and replaced by new values. The comparison statements are shown each time using new values in the Boolean expression. Let's look at the image. Y equals 1 goes to 1 is less than 5, which is true, print message. Y goes to 2. 2 is less than 5, true, so print message 3. 3 is less than 5, true, print message goes to 4. 4 is less than 5, true, print message goes to 5. 5 is not less than 5, so that's false, and exit the loop. The for loop has the following elements. The for loop has the following elements: a control variable that facilitates the entire mechanics or workings of the loop, a Boolean expression that checks to see whether the control variable is within range, and a counter statement to change the value of the control variable. We will examine each of these elements in order to understand the structure of the for loops. The control variable. A control variable is a variable that does the work of the loop. In the previous example, it was the variable y. It must be declared first and then given to an initial value before the loop starts to spin. The control variable is then used in a Boolean condition to determine whether the loop spins or not. Just like other control statements, the ifs and the if and the if else Boolean expression must be true for anything to happen. The loop will be exited when the Boolean expression becomes false. The general idea is that a control variable is compared with some limit, an upper limit or a lower limit. When it is compared with an upper limit, the control variable is checked to make sure that it is still less than the upper limit. Control variable less than upper limit. As long as this is still true, the body of the loop is executed. After the body is executed, the control variable is increased. Conversely, the control variable could be compared to a lower limit in the following manner. The control variable would be checked to see that it is still greater than a lower limit. Control variable greater than lower limit. As long as that is true, the body of the loop is executed. Then the control variable is decreased. See figure 7.8. Figure 7.8. The control variable is shown in each example, compared to an upper limit or a lower limit, respectively. Depending on the value of the Boolean expression, either the body is executed and the variable changes, and the variable changed, or the loop is exited. Let's look at the figure. Control variable is less than upper limit, less than or equal to. Well, if it's true, then it executes the body of the loop, and the control variable is increased. If it's false, exit the loop. If the control variable is greater than or equal to the lower limit, if it's true, then execute the body of the limit of the loop, and the control variable is decreased, or if it's false, exit the loop. Okay. Part of the structure of the syntax of a for loop is assigning the control variable its initial value, that is, the value it should have at the start of the execution of the loop. Then, during the loop's repeated executions, the control variable changes value. Finally, when it reaches the last value and the Boolean expression becomes false, the loop is exited. The initial statement. The first statement contained within the parentheses of the for loop is the initialization statement for the loop's controlled variable. You must declare the variable before giving it to its initial value. In separate statements or in one combined statement. Notice that I have left the rest of the for loop statements blank for now. This syntax grammar shows how to assign an initial value to the control variable. Declared, then assigned, declared and assigned in the same statement. Initial x for x is equal to 1, the other side, for int x is equal to 1, Declared then assigned, initial int y for y is equal to 100, Declared and assigned in the same statement for x int y is equal to 100, Notice that in the first example, the initial value of the state of the variable was 1. It is easiest to start counting at 0 or 1, and that is the reason why most for loops will initialize the control variable to one of these integers. The second example uses a large number as its initial value. You will soon see why. Note, the for loop's control variable is always an integer. The Boolean expression. The next statement used in a for loop is the Boolean expression, which must be true in order for the loop to execute. We first examined Boolean values in chapter 6. Since a Boolean expression has either the value of true or false, we can use that value for controlling whether a loop will execute or not execute. Think of the Boolean expression as the permission granted or denied for the body of the loop to be executed. If the Boolean expression is true, then we enter the loop and execute all the statements within its control. If the expression is false, then we exit the loop. To leave the loop means to go to the first line of code immediately following the for loop block. For int count equals 0, count is less than 25, count equals count plus 1. / open bar, / body of loop is here, for example. See out, I will not chew gum in class, and L. Closing. Program continues here after loop is executed. Let's examine each of the previous examples and write a Boolean expression using the control variable. In our first example, we initialized x to be 1, and now we will set the expression to show that x should be less than 5. As long as x is less than 5, we want to execute the loop. It will look like this. For int x is equal to 1, x is less than 5. Here is another example. We will initialize the variable y to 100 and use a Boolean expression that shows y greater than or equal to 0. Notice the use of the equals sign in the condition. This means that when y reaches 0, it will still spin one more time because 0 equals 0. In that case, it will execute the body of the for loop one last time. For int y is equal to 100, y. Note, y is equal to, for int y is equal to 100, y is greater than or equal to 0, ... Note, the body of the for loop is entered only when the Boolean expression is true. The counter statement. The counter statement we mentioned previously is the third statement used in the for loop. There are two types of counter statements. One that increases the value of a variable, and one that decreases the value of a variable. Increases the variable, decreases the variable. X is equal to x plus 1, y is equal to y minus 1. Count equals count, answer equals answer minus 1. Age equals age plus 1, sum is equal to sum minus 1. Using our previous examples, we insert the third statement, the counter statement, into the for loop syntax. The third statement will be executed after the body of the loop is executed. Imagine that there are 4 parts to the entire for loop. These 3 statements and the body of the loop. Let's number them in the order in which they happen. For x is equal to 0, first goes to x is less than or equal to 100. Second, open brace, open book, open bar. Body of the loop, third, close bar. X is equal to x plus 1, fourth. So the for loop executes the first 2 steps, the first and second, and then enters the loop as its third step and executes the body. Lastly, it executes the 4th statement, the counter statement. Keep in mind, too, that the initial statement that sets the control variable's first value happens only once. The second time you loop back for instructions, the computer will only execute the second, third, and 4th steps. See Figure 7.9. Figure 7.9. The second, third, and 4th steps are shown in sequence, repeating each time the loop spins. X is equal to 0 happens once. Goes to x is less than or equal to 100. Goes to body of loop. Goes to x equals x plus 1. Goes to x is less than or equal to 100. Goes to the body of loop. Goes to x is equal to x plus 1. Goes to x is less than or equal to 100. Goes to body of loop. Goes to etc. Here is another variation on the syntax of a for loop. The declaration of the control variable is outside the for loop. Int y, semicolon, for y is equal to 0, y is less than or equal to 100, y is equal to y plus 1. Example 1. Let's start with an example of a problem that would utilize a for loop. These programs are usually ones where you know ahead of time how many times you wish to do something. In our example, let's print the numbers 1 through 10 on the screen. The first thing to notice is that we know we want to do something 10 times, printing those numbers on the screen. for x is equal to 1, x is less than or equal to 10, x is equal to x plus 1, open brace, C out, x and L, closing brace. Now let's step through the for loop one line at a time, just like a compiler would do. First, x gets the value 1. Then that value is checked to see whether x is less than or equal to 10 is true. Because this is true, the body of the loop, only one statement, the printing statement, is executed. The next statement, x is equal to x plus 1, changes x's value from 1 to 2. After that, recall that the initial statement is not executed again. We go directly to the Boolean expression to see that x is less than or equal to 10. Yes, because 2 is less than or equal to 10. It is true, so we execute the Boolean, we execute the body of the loop and print the number 2 on the screen. After that, x changes from 2 to 3. This pattern continues. See Figure 7.10. Figure 7.10. The sequence of events in the for loop are shown as the control variables values are repeated and are repeatedly changing. Control variable, Boolean expression, value, resulting action. X, 1. 1 is less than or equal to 10, true, 1 is printed. 2. 2 is less than or equal to 10, true, 2 is printed. 3. 3 is less than or equal to 10, true, 3 is printed. 4. 4 is less than or equal to 10, true, 4 is printed. 5. 5 is less than or equal to 10, true, 5 is printed. 6. 6 is less than or equal to 10, true, 6 is printed. 7. 7 is less than or equal to 10, true, 7 is printed. 8. 8 is less than or equal to 10, true, 8 is printed. 9. 9 is less than or equal to 10, true, 9 is printed. 10. 10 is less than or equal to 10, true, 10 is printed. 11. 11 is less than or equal to 10, false. Exit loop. Example 2. In a second example, utilizing a for loop, let's look at a list of 20 numbers, and for each number we will print a message on the screen indicating whether that number is even or odd. Here we will use the if statement from chapter 6 to help the compiler decide whether the number is even or odd. Int x, for x is equal to 0, x is less than 20, x is equal to x plus 1. Opening brace. If x mod 2 is equal to 0, see out x is even, end line. Else, see out is x is odd, end line, star. We were able to use the if else statement from chapter 6. See how useful it is, star. Did you notice the syntax for the extended comment about above? Here is the output from running the preceding code fragment. Each number will be printed with the appropriate tag is even or is odd. 0 is even, 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even, 7 is odd, 8 is even, 9 is odd, 10 is even, 11 is odd, 12 is even, 13 is odd, 14 is even, 15 is odd, 16 is even, 17 is odd, 18 is even, 19 is odd. You will not see 20 on the screen, because the loop is exited before 20 is used in the body of the loop. Recall that the Boolean condition was x is less than 20. Once x hits 20 or becomes 20, the Boolean expression becomes false and the loop is exited. On the CD, the complete program that prints even or odd next to a list of numbers. The complete program that prints even or odd next to a list of numbers. The conditional loop. A conditional loop is a loop that does not spin a fixed number of times. It spins only on the condition that some Boolean expression is true. You do not know beforehand how many times it will spin. What the Boolean expression is, while the Boolean expression is true, the loop spins. Once the Boolean expression changes from true to false, the loop, upon finishing the body, stops. The while loop. To understand the while loop, first we need to look at an analogy. Imagine that you enter a large office room where you must get all this work done. You need to get into the room and clean each desk in the room. You are a very methodical worker, so you only clean one desk at a time. This means that you wipe off the desk, sweep under it, and empty the waste barrel for each desk rather than empty all the barrels at once or sweep under all the desks first. Another stipulation about how you work is that you can only work in the room if the light is on. It's on an automatic timer. You go to the door and check to see if the light is on. If it is, you enter the room and start to work. You will work in the room as long as the light is on. At some point you expect the lights to go off, since they are only on an automatic timer that someone else set. When the lights go off, you finish the work at the desk you are at, and then you leave the room. In a sense, you work while the lights are on. You do each task as outlined in the following description. While lights are on, check the lights here. Open brace. Enter body of loop to do your work. Clean the top of one desk. Pull out the chair. Sweep under the desk. Push in the chair. Empty the barrel next to the desk. Closing brace. You have to finish all the steps at one desk, even if the lights go off while you're still doing one of the tasks, like sweeping under the desk. Once the lights go out and you have finished all the work at one's desk, you leave the room. However, if the lights are still on, you go on to the next desk. They actually might have gone off while you were sweeping under the desk. Remember, because of your odd work, habits. You can't leave the room until you finish all the work at one desk. Now back to our while loop. The while loop will spin as long as some Boolean expression is true, analogous to our lights being on. Inside the body of the while loop are the statements you wish to execute. Within the body of the loop, there must also be a programming statement that triggers the Boolean expression to change, like the lights going off with an automatic timer. When that happens and control passes to the top of the loop, the Boolean expression will be false and we will leave the loop. Notice the sequence of arrows indicating how the loop is controlled. Once the last statement in the body of the loop is executed, we bounce back up to the top of the loop to see whether the Boolean expression is true. Pointing to the right. While Boolean expression is true, pointing downward, opening brace, pointing upward, the body is body of a loop. Pointing down, statement 1. Pointing up, statement 2, etc. Pointing down, ... pointing up, pointing to the left, closing brace. To expand on this loop structure, we need to add some key statements. A counter statement in the body of the loop will allow both loops to function like for loops. That is, the number of times they spin can be counted as they are spinning. Let's use the analogy to draw a picture of the while loop structure. See Figure 7.11. Figure 7.11. The while loop is shown both in the analogy of the office worker and in a programming context. While lights are on, opening brace, work at one desk, ... Did the lights go out? ... Finish work and at one desk, closing brace. While Boolean expression is true, opening brace, execute the steps, ... Did the Boolean expression change? ... Finish all steps within the braces, closing brace. Figure 7.11. The while loop shows both in the analogy of the office worker and in a programming context. Let's continue to refine the analogy. When you are in the office, you only work while the lights are on. However, you can only check the automatic timer after you finish the work at one desk. The while loop operates the same way. You can only check the Boolean expression at the top of the loop. This analogy is used to emphasize how the while loop does its work. It only checks the Boolean expression at the top of the loop. For this reason, it is called a pre-test loop. A pre-test loop is where the Boolean expression is checked first before entering the body of the loop to execute its instructions. At some point inside the loop, some statement will cause a future evaluation of the Boolean expression to be false. After the body of the loop is executed, the control goes back up to the Boolean expression, and since it is now false, the compiler exits the loop and goes to do the next line after the loop. The do-while loop. With the do-while loop, the same analogy can be applied. In the office room analogy for the do-while loop, you walk inside the room and start cleaning right away, whether the lights are on or off. After you've done the work or the tasks for one desk, you look up to see if the lights are on in the room. When they are, if they are, you stay in the room in the loop and do the same work on the next desk. Do opening brace. Enter room to do your work. Clean the top of one desk, pull out the chair, sweep under the desk, push in the chair, empty the barrel next to the desk, closing brace, while lights are on. The analogy is a little different from the one used in the while loop, in that you only look up to check the light situation at the end of the loop, not at the beginning. At the end of the work done at one desk, you look up to see if the lights are still on. If so, you will move to the next desk. For this reason, the do-while loop is called a post-test loop. You test the condition, i.e. the lights, after the body of the loop. Do, opening brace, executes the body of a loop, closing brace, while Boolean expression is true. Two examples from a programming perspective. The best way to understand these loops is to start using them. Let's look at an example using each loop. In each example, try to identify the Boolean expression used to control the loop. Although there are many situations where any of the three loops could be used, each example uses a loop which works particularly well in the context given. Example 1. A good example of the while loop is when you use it to get some specific input from the user. Let's use it to verify a password entered by a user at an ATM. This is a good example, since we do not want to grant access to an account unless the password is correct. We also want to give the user a chance to correct his password. The while loop would test the password initially to make sure it is correct. Once it is correct, the user would be allowed to leave the loop. The while loop would spin as long as the password was incorrect. Here is an algorithm for verifying the user's password. Then the code fragment that executes the algorithm follows. The algorithm. 1. Ask the user for his password. 2. check to see if his password is correct. 3. If it is correct, go to step 6. 4. If it is not correct, ask the user to type it again. 5. Go to step 2. 6. Allow the user access to his account. String response. Password ... Password would be assigned before we get to this section. Cout. Please type your password and L. Cin. Response. While response not password. Opening brace. The loop will spin when the password is incorrect. Once it is correct, the user will be released from the loop. Cout. Your password is incorrect. End line. Cout. Would you please type it again? End line. Cin. Response. Closing brace. Example 2. Here's an example where we simulate the game playing scenario we spoke of earlier in the chapter. Let's surround the code for a game with a loop that depends on the player's willingness to play the game. We will use the do while loop in this example. The algorithm: 1. Play the game. 2. Ask the user if he would like to play again. 3. Check to see whether his answer is yes. 4. If the answer is yes, go to step 1. Otherwise, stop. Do. Opening brace. Here is where all the code for the game belongs. It is probably several pages long. You do not need to know that. Cout. Would you like to play the game again? End line. Cin. Response. Closing brace. While response equals yes. The user plays the game at least once because of the way the loop is designed. You enter the loop no matter what because the Boolean expression, which is controlling execution, is at the bottom of the loop. Then we ask the user whether he wants to play again. Only if he says yes do we execute the do loop and a second time. Then he must say yes again in order to play the game a second time. He'll have to say yes before he can play the game again. You have probably experienced this kind of loop when you played a game. Would you like to play the game? Yes, game is played in here. Then again, would you like to play the game again? Yes, and again. Would you like to play the game again? Yes. One more time. Would you like to play the game again? No. Then it stops. In fact, it would stop for anything that did not look like yes, which encompasses a lot of responses. No, no, yes, yes, why, maybe, okay, and so on. Would all cause the loop to stop because the Boolean expression response equals yes would be false. Remember, the conditional statement is case sensitive and computers have no intelligence unless you provide it programmatically. Using a conditional loop with a counter statement. Any while loop to do while loop can be used to simulate the actions of a for loop. What that means is the while loop is set up so that it has all the elements of a for loop. That is, it has a control variable, a counter statement, and a Boolean condition dependent on the control variable. Unlike the for loop, which has these three statements at the beginning of the loop, the control variable is initialized before the while loop, and the counter statement is within the body of the while loop. The Boolean condition is at the top of its loop, however. int x is equal to 1, while x is less than 10, opening brace. Body of the loop, cout is less than, x is less than, and l. Counter statement to increase x is equal to x plus 1, closing brace. As the loop spins, x increases and gets closer to the upper limit, which is 10. Look at the output from executing this loop. 1, 2, 3, 4, 5, 6, 7, 8, 9. You will not see 10 on the screen because once the control variable becomes 10, the Boolean expression at the top of the loop is false. 10 is less than 10 is false, and we exit the loop. Thus, we never see the 10 on the screen. When a while loop is used with a counter statement, the counter statement acts as a clicker and counts the number of times the while loop spins. Since the Boolean expression is used to control the while loop, it must depend on the variable used in the counter statement. We can do a similar example with the do while loop. Recall that the Boolean expression will be at the bottom of the loop. Like the while loop, we need to set the control variable before we enter the loop and put the counter statement within the body of the loop. Int x is equal to 1. Do, opening brace, body of the loop, cout is less than, x is less than, and l. Counter statement to increase x is equal to x plus 1, closing brace, while x is less than 10. You will get the same output as you had in the while loop. Again, you will not see 10 in the output because the loop is exited before 10 can be printed on the screen. 1, 2, 3, 4, 5, 6, 7, 8, 9. Summary. I introduced the loop which surrounds one or more programming statements, referred to as the body of the loop. The loop is used for repeating steps in a program. It is another example of a control statement, since the compiler is forced to stay in a loop rather than go to the next line. Another useful statement is the counter statement, which has this syntax: variable equals variable plus 1. Some variable gets its present value plus 1. This statement is used to increase the value in a variable, and it is also used in the context of loops. When a counter statement is used in a loop, it allows the variable to become bigger, or conversely, smaller, so that the Boolean expression controlling that loop can be altered. We can examine two kinds of loops: fixed iterative and conditional loops. The fixed iterative repetitive loop executes a known or fixed number of times. The conditional loop will spin as long as a Boolean expression is true. The for loop is a fixed iterative loop. It spins a known number of times. The loop has three parts besides the body of the loop. A statement initializing a control variable, assigning it a first value, a Boolean expression, and a counter statement using the control variable. Two conditional loops are the while loop and the do while loop. The while loop is an example of a pre-test loop. The while loop is an example of a pre-test loop. A Boolean expression is examined to see if it is true, before the loop is entered. The do while loop is an example of a post-test loop. The condition is tested after the loop is executed. Both the while loop and the do loop can be used to replace a for loop by inserting a counter statement into the body of either loop.